Hello and welcome to a live stream of Chemistry 221. This is for the summer course, so we're going to go really fast paced. Today we're going to be covering chapters 1 and 2, focusing mainly on kind of isotropic abundance and dimensional analysis, stuff like that. I'll start out by saying my name is Travis. I am a tutor and chemistry tutor at the Learning Center at Portland State. I can also post a few useful links in our chat window. So the first one that I like to post in there is a link to our Learning Center's website. So definitely check them out, and just whenever you're looking for any resources, tutoring with schedules for tutors and stuff like that, you can find stuff like that there. You can also follow them on Facebook and Instagram to get automatically notified anytime we have new resources available, such as this live stream. So there's some links for that in there as well. So let's just jump ahead and get started with what we're doing today. So I'm going to jump in here. There we are. So today, I'm going to start out by just kind of talking about the different phases of matter. Some of this should be fairly familiar with. You should be fairly familiar with. My screen's a little off. Okay. So there's a solid, a liquid, and a gas phase. The solid kind of has that fixed shape and volume, similar to like an ice cube. It doesn't really change a lot based on its environment until it heats up and starts to melt. And then it turns into a liquid. The liquid has a finite volume to it, so it doesn't change in volume, but it will change shape to fit the container that it's holding. We see this if we pour water in a glass and then pour it onto the table. It spreads out amongst the table. We can also see a gas. If we heat it up enough, it changes phases into the gas form. In this case, it actually expands to fill the volume of the object that it's in. So if you were to take this little Erlenmeyer flask and put a balloon on top of it and pop that cork, the gas would actually expand to fill the balloon to have the same pressure throughout that whole volume eventually. These are the common phases of matter. It's liquid, solid, and gas. Talk a little bit about the periodic table real quick as well. You're probably familiar with this. This is a really good thing to get really familiar with because the periodic table is going to be incredibly useful over time. My computer is freaking out on me. So let's see if I can reset a few things. Okay. So the periodic table is set up in kind of groups, columns, you could say. Group 1 being on the left side over here. Group 18 being on the right hand side, and different periods kind of going down this way. They're oriented in a certain way where common elements are kind of grouped together in different ways. We have the alkali metals and alkali earth metals over here. Your transition metals kind of in the middle here, and you kind of have your P group over here. You'll learn more about that when we get into orbitals and stuff like that, and then your noble gases down here. These are also the lanthanum and I can never pronounce these acinides, lanthanides, and acinides. Basically, these two rows stick in here and kind of spread it all out, but then it gets really stretched out, so we combine it and just put those two rows down below. Each element on the periodic table follows this basic nomenclature down here, where the symbol, in this case is hydrogen, is listed in the middle. The atomic number, which is equal to the number of protons plus the number of neutrons in there, is up in the top left corner. And no, sorry, the atomic number is the number of protons in general. So hydrogen has 1 proton to it, so it's going to have up there. You can see like carbon has 6 protons in it, so it has a little 6 up in that top corner. The atomic mass, this is actually an average, which is important to know. That average atomic mass for hydrogen is 1.008 grams per mole. And that's an average because there's different isotopes for things. So we're going to get into isotopic abundance a little bit later. And then the name of it's kind of underneath. So these are the common things we use. This periodic table is really useful. So find a version of it that you like. Keep it in a place that you can always refer back to it commonly. Let's go on here. Talk a little bit about the base system units. These SI units are standard units. If you're not familiar with these yet, it's really useful to get used to some of these here. Mainly I'll give it a little highlight. The length, I think, is really important. is a meter. You also see kilometers, and we also see different metric conversions and units of that, like the nanometer, micrometer, millimeter, and so on. And we'll go into those in just a second. Mass is usually in kilograms, but in chemistry, a kilogram is a really big thing, so we deal with grams often instead. There's also time, temperature, which you're pretty familiar with. Temperature, if you notice, is in Kelvin. Kelvin is equal to, say, 273.15 Kelvin is equal to 0 degrees Celsius. It's a simple conversion from Kelvin to Celsius. To Fahrenheit, it gets a little bit more complicated, but there's equations in your book, really easy to run through. The mole of a substance. This is something fairly unique to chemistry, but it applies all over the place, really. And a mole is a number of objects, and that number is a rather big number. It's actually equal to 6.022 times 10 to the 23rd power. So that's a whole lot of something. And anytime we talk about a mole of carbon atoms, it's that many carbon atoms in one group. We talk about a mole of hydrogen atoms, it's that many carbon or hydrogen atoms in one group. You can have a mole of pennies, you can have a mole of sand castle, so you can have a mole of anything. It's really just a number of stuff. Go into metric unit conversions. These are some of the common ones. There's a big table here. I pulled this straight out of the OpenStax book in chapter 1. The common ones you really want to be able to identify are kind of the micro, milli, centi, kilo, and maybe even nano in there. Those are the ones here that are going to use commonly within this chemistry course. You're going to have a lot of centimeters, you're going to have a lot of millimeters, milliliters, and so on. So it's really good to learn how to convert between one and another, because anytime you're working with different numbers, you want to make sure they have that same base unit. There's also a few derived units, which are just kind of combinations of these guys. First one we'll say is volume. So volume, you might be somewhat familiar with. It's just kind of the area, or not area, it's the volume of a container. So it's length times width times height, for example. Usually it's going to be in liters. Oops. It's going to be in liters, which is, we can say, equal to, I think it was 0.001 meters cubed. So that's a 0.001 meter times 0.001 meter times 0.001 meter, and so on. We could also convert that to milliliters. So we can think of 1 milliliter, which is equal to 1/1000th of a liter. Oops, that liter should be up top. Boom. 1/1000th of a liter, which is also going to be equal to a centimeter cubed. And these are one of the conversions you'll see very often. It's really important to remember that 1 milliliter is equal to 1 centimeter cubed. And the conversion from liters to meters cubed is also fairly useful, because sometimes they'll kind of throw that at you as well. And now I'm going to jump into significant figures. I'm going to throw a few examples out and some rules that I like to follow. So with significant figures, there's basically two types of calculations we're going to deal with in this course. Any type of calculation has a rule for the significant figures for it. It's good if you run into these weird calculations to look up what that rule might be. But for the most part, we're going to deal with two different types. The first type is addition and subtraction. And I can give a few examples of these guys here. So when you have significant figures and you're doing the math behind them, we can use, say, I have this example 5.756, and I'm going to add to that 0.23. And anytime you have addition and subtraction, the rule I like to use there is to round to the last common significant figure. To last common sig fig. So in this case, what that means is the last common significant figure is going to be the second decimal place. So I just draw a line right down there. We still do the math for everything, all the numbers that we have. In this case, 6 plus 0 is 6, 5 plus 3 is 8, 7 plus 2 is 9, and we end up with that 5 plus 0. But we kind of tourniquet it off after that, and we round up this value up now since we have a 6 there. So this is really going to equal 5.99. And notice here we had kind of 3 decimal places. And here we had 2 decimal places. Just say 2 places. So our answer is going to have 2 places. Because that last significant, the location of that last significant digit is what we're going to round to. The same thing is going to be true in subtraction. Taking similar numbers, this time I'm going to throw a 5 there. I'm going to subtract. So 6 minus 0 is going to be 6, 5 minus 3 is 2, 7 minus 2 is 5, 5 minus 5 is 0. And in this case, we still kind of draw that line down there, and we have to round based on that. So this is really going to be equal to 0.52 or 53 because we round up. And notice we're going out to 2 places again because that's the last common place. But notice also in this case, this number here had 4 significant figures to begin with. It went out 3 decimal places but had 4 significant figures. The second one, 0.23, had 2 significant figures, even though it went out 2 decimal places. And our answer is going to have 3 significant figures. So it's really determining based on the last common sig fig that we have to look at. For multiplication and division, which is the other type that we're going to be dealing with, we're really going to look at, in this case, the answer should use the sig figs corresponding to the factor with the least amount of sig figs. So what does that mean? That means if you're multiplying a number with 2 sig figs times a number with 3 sig figs, your answer is going to be 2 sig figs. The lower amount of significant figures, that's what you're going to round your answer to. So some examples there. We have 0.150 times, I'll just say 3.0. And notice in this example, this one here is 3 sig figs, and this guy here, 2 sig figs. So when I do my multiplication, I do 0.150 times 3.0. That's going to equal, I have a scientific notation here, so that's 0.45. Say 0.450. And we really want to round it to 2 sig figs. So really, my final answer is going to be 45. Because I want it to be equal to the number that had the least amount of sig figs. Looking at division, we can say 0.150 divided by 3.0. So if I do this on my calculator, and it's important to actually calculate with all the digits you have and just round your final answer. So if you're doing a problem where you have multiple stages, at each stage, don't round your answer. Leave it complete, and then at the end, figure out what your significant figures need to be. So in this case, this is equal to 0.005. That's what my calculator tells me. But I know I need this being 3 sig figs, this guy being 2 sig figs. I need to have my answer in 2 significant figures. Right now, 0.005 Oh, sorry, I have an extra 0 in there. Well, 0.05 is only one significant digit. These leading zeros don't count. They're not significant. Just this one is right now. We need to add another 0 in there. The trailing zeros are always going to be considered significant digits if it's after that decimal place. So now my answer is in 2 sig figs. I'm going to try a problem out of the book. It says perform the following calculations and report each answer with the correct number of significant figures. So the first one is 62.8 times 34. So if we look at this, we can see this is 3 sig figs and this is 2. So my answer should be to 2 significant figures. So now just pulling up my calculator, we can do the math. 62.8 times 34 is equal, and move that decimal place 3 to the right. This is going to equal, say, 2135.2, but that's 2 significant figures is what we need that at. So I can actually write that as scientific notation, leaving it there, just cutting it down to 2. That's 2.1 times 10 to the third. For part B, it's the same idea, but now we're adding instead of multiplying. So we really have to look at the last common significant figures. This is 3 decimal places. This is 4 decimal places. This is 3 decimal places. So once we find our answer, we need to round our thing to 3 decimal places. So doing that, 0.147 plus 0.0066 plus 0.012. So that's going to equal 0.165. I'm going to round that one up actually. 656 goes to 66. Because you always have to round up to that last significant figure that you're looking for. The next one, it's all multiplication, so we're going to use the lowest value of sig figs. Not the lowest number, but the lowest number of sig figs that's on there. So in this case, we have 2 sig figs, 2 sig figs, and 4 sig figs. So our answer needs to be in 2 significant figures. Doing the math, 38 times 95 times 1.792 is going to be 646.912, but we want 2 significant figures. So I can leave this in scientific notation. It's usually the easier way if you have a value that's higher. And that 4 needs to actually be rounded up to a 5 because the next digit is a 6 times 10 to the third. The next one uses subtraction. So again, we need to look at the last common significant digit. In this case, we have 0 decimal places for that 15, 2 for the 0.15, and 4 for the 0.6155. So doing the math, 0.6155, we get 14.2345. So since we have to round at 0 decimal places, so we have to round kind of at the whole number. So this is going to equal rounding 14 down to 14. For part E, we have multiplication and division. They kind of follow the same rules, the least number of significant figures. So looking at this, we have 3 there. This one is 0.0500. Only the last 2 zeros are significant. The first ones are all leading. So we can say that's 3 sig figs as well. So is the bottom. So we can just do our math and round up to 3 sig figs. And this is going to be 0.918. I'm going to skip the next 2 because they're very similar to what we did, but part H, that one is a tricky one because it has subtraction in the numerator and then we're dividing. So we need to pay attention to what the significant figures of the numerator should be before we divide, and then do the division and find out our final significant figures. So in this case, I could do the subtraction first. If I do 88.5 minus 87.57, that is going to equal 0.93. But notice the last significant digit. This has 2 decimal places. I'm sorry, this has 1, and this has 2. So the last significant digit is going to be that first decimal place. So really, I can write this 3. I'm going to write it in a different color because it's still there, but it's not a significant value. So then we can divide that number now by 45.13. And doing that, 45.13 gives us 0.02. 0.02. Notice my answer is to one significant figure. So we're going to move on to some conversion factors and dimensional analysis. This table here is some common conversion factors. Anytime you're ever wondering like how many feet are in a mile or how many meters are in a kilometer and stuff like that, a quick Google search will usually get you the right answer. There's also a lot of tables and stuff in the book and available online as well. So we can use these to answer a few different problems. I've picked out 3 problems from the textbook here. And so in this first one, a very good 197-pound weightlifter lifted 192 kilograms in a move called the clean and jerk. They want to know what is the mass of the weight lifted in pounds. So the mass that was lifted was 192 kilograms, but we want to know what that weight was in pounds. So we need to convert that to pounds. So anytime we're converting to pounds from kilograms, we need that common conversion. This up here, this tells us what that is. So 1 kilogram is equal to 2.2046 pounds. And we can write that in a fraction where 1 is over the other. So if I were to write that as 2.2046 pounds divided by 1 kilogram, the value of this fraction is really equal to 1. Because the numerator is equal to the denominator. Anytime you have that, your fraction is equal to 1. But we can use that to multiply to our 192 kilograms to get our answer in pounds. And notice we can separate out kind of the units from this, and we can do unit math in the same way, the dimensional analysis. We work in the same way as variables would. So in this case, kilograms is part of the numerator here and the denominator down here. So they can cancel because kilograms over kilograms is going to equal 1. They cancel out. And then we can just do this math, multiplying 192 times 2.2046. So that's 192 times 2.2046. And that's equal to 423 pounds. Notice I stopped there because this is 3 sig figs. And whenever we're converting, this conversion ratio never changes our significant figures, no matter what it is. It's always going to be an absolute value. It's going to be an exact value. There's no approximation there. So we don't use it to change it. Our answer should be the same sig figs as our original problem. This next one here says many laboratory tests are run using 5 microliters of blood serum. What is the volume in milliliters? So those values then is 5.0 micro, which looks like a little U and an M combined, liters of blood, and we want to convert that into milliliters, ml. So looking at, we can go back to our conversion table here, and micro is 10 to the negative 6 meters in this case, because we're talking about liters. So 10 to the negative 6 liters, and milli is 10 to the negative 3 liters. So we can use those ratios to figure out then what this would be. In doing that, I can separate out this and say 5.0 microliters. I'm going to multiply that times that ratio that we were talking about, which is 10 to the negative 6 microliters per liter. And then I can multiply it by 10 to the negative 3 milliliters per liter. And watch what my unit conversions do. My dimensional analysis cancels this and this. The microliters cancel out, so do the liters, and my answer is going to be left in milliliters. So that's what I'm looking for. So anytime you're doing this, when you write that ratio, you want what the units you have to be on the denominator of what you're converting. The units you want to be at the numerator. And here I had to do it twice. So first I converted to liters, and then I converted from liters to milliliters. And you see the ultimate result of this is we're basically, I'll write it out here, this is basically 5.0 times, and then we have 10 to the negative 3 over 10 to the negative 6. And when we do that fraction, we take the exponent of the numerator, subtract the exponent of the denominator. Well, that's that's negative 3 minus a negative 6, which is going to be a positive 3. So our answer is going to be 5.0 times 10 to the third power. And this makes sense because we're converting microliters into milliliters. We have a small unit into a bigger unit. So we're going to end up with a larger number. You know what? I did this wrong. I am sorry. This should be up here. Okay, let me correct myself now. So 1 milliliter, or 1 microliter, this is my mistake, just talking too fast. 1 microliter is equal to 10 to the negative 6 liters. So I had the units in the right place, but I had that 10 to the negative 6 in the wrong place. In the same regard, 1 milliliter is equal to 10 to the negative 3 liters, which means this ratio is off. This should be 10 to the negative 6 over 10 to the negative 3. So when I do negative 6 minus a negative 3, I should get 10 to 5 times 10 to the negative 3. And this unit should be in milliliters. Apologize for that. But that's going to be the answer we're looking for this. So yeah, make sure the milliliter, or the microliter in this case, is going to be equal to 10 to the negative 6 liters. That's what our chart over here is saying, that micro is equal to 10 to the negative 6, and milli is equal to 10 to the negative 3, where these factors are going to be in your SI unit, that liters or meters or grams or something to that effect. So that's what we have here. That's liters, so we have 10 to the negative 6 liters. We have 10 to the negative 3 liters. All right, the next one has to do with calculating masses based on density. And for density, I'm going to use D for density is going to be equal to the mass divided by the volume. And that's a key thing to understand, is because whenever we have these units, you see like grams per centimeter cubed or grams per milliliter, kilograms per liter, stuff like that. They're all going to be units of density, where it's mass divided by volume. And we have to make sure we have the right units for these to get the answer in the units that they want. So for the first one, part A, we know the mass is, or we want to find the mass when the volume is equal to 4.00 centimeters cubed. And we know that the density is equal to 0.97 grams per centimeter cubed. So just looking at the units, since what we want to know is mass, and mass is in grams, we can multiply these two together because the centimeters cubed will cancel out when we do that, and we'll be left with just grams. So let's do that. If 4.00 centimeters cubed times 0.97 grams per centimeter cubed. Let's notice we have the numerator and the denominator, so those units are going to cancel out. Our final answer is going to be in grams, which is what we're looking for. So let's just plug it into the calculator, 4.00 times 0.97. You might ask yourself, what is the significant figures here? Well, we have 2 sig figs, and we have 3 sig figs. The zeros in that 4.00 are trailing. They're going to be significant figures. The 0 in the 0.97 is a leading 0. It's not significant. So our answer needs to be in 2 sig figs. So it comes out to be 3.9. The units are in grams. We always got to include those units to make sure we're in the right place. And if you're ever not sure where to go with it or how to get to the value, try to follow the units in the math and dimensional analysis, and it should lead you in the right direction or give you an idea of what that right direction is. I often will do that dimensional analysis, make sure I have the right units before I actually crunch all the numbers, because if you don't have the right units, you need to rearrange things. Something's gone wrong. So that's the basics of dimensional analysis. You can take that to the higher level. It gets more and more complicated, but just take it one step at a time, looking at the units at every step. We're going to go on, this is the periodic table of elements again. We're going to use that now to start talking about the different isotopes that we can run into when we're dealing with chemistry. So here, number 12 in your textbook for chapter 2 is write the symbol for each of the following ions. So the first one, part A, and I should note I have a few general guidelines on how to find the atomic number, the mass number, and the number of neutrons. The one that's left out from here is electrons. And anytime you have a neutral atom, the number of protons and the number of neutrons is going to be equal to each other. So if you have a charge to that, basically you either have extra electrons or you're missing electrons. So we can use that to our advantage to use the charge and the number of electrons to find our mass number, and that, or to find our atomic number. So for part A, they're telling us the charge is +3. The electrons, there's 28 electrons floating around in there, and we have a mass number of 71. And if you remember, I can draw a basic thing here, where Z is the number of protons. Your mass number we call A usually. It's really the number of protons plus the number of neutrons. And we have a charge, which would be just up here, which is plus or minus something, whatever charge you have. So we can find the number of protons is going to be equal to the electrons plus the charge. Because if the charge is positive, that means we're missing electrons in there. Electrons are negatively charged particles floating around the nucleus. So in this case, we have 28 plus 3, which is equal to 31. Now that we know what Z is, equal to 31, remember that's the number of protons, and that defines what the element is. So we can go to our periodic table, and we can search for number 31. So just that top left corner, we can see here is gallium, Ga. So now I know when I'm writing my symbol, Ga, I need to know it's going to be 31. Ga is always going to be 31, so it's a little redundant in that case, but we write it in there anyways. The mass number, A, is going to be 71. and the charge is going to be 3 plus. And that gives us that symbol for gallium. For part B, we want an ion with 36 electrons, 35 protons, and 45 neutrons. Well, 35 protons, that right there tells us Z. So I can go over to here and see, yep, there it is, bromine has 35 protons. 35 is the atomic number. So I know I'm going to have bromine 35. I don't know the charge, and I don't know the mass number just yet, but I know that mass number A needs to equal the protons plus the neutrons. So we know it's 35 plus 45. 35 plus 45. Which, if my math is correct in my head, it might not be, is 80. So I'm going to write 80 up on the top for A. Now to find out the charge, like I had said earlier, a neutral atom has a charge of 0 and an equal number of protons and electrons. So we can find out what that is by finding the difference in there. If there's more electrons than the protons, it'll be a negative charge. If it's less electrons than the protons, it's going to be a positive charge. Because protons are positively charged, electrons are negatively charged. So we can say the protons are 35, and we can minus from that the electrons, 36, which is equal to -1. So that means our charge is, say, just negative or 1 negative. Part C, we have an ion with 86 electrons, 142 neutrons, and a +4 charge. So again, we can say that Z is equal to the electrons plus the charge, which is 86 plus 4. 86 plus 4 equals 90. And we can find element 90 with an atomic number of 90 would be thallium. Thorium. I said that wrong. 86 electrons plus 4. Yeah. So that would be thorium. TH, was it? Yeah. TH. Okay. And we know that the, neutrons are 142. So that would be 90 plus 142 is going to equal A, that mass number, which in this case, 90 plus 142 is equal to 232. Oh, we've got my little 90 down in the corner. And we know the charge is a 4 plus. And there is part C. Part D, last one here, is an ion with a 2 plus charge, an atomic number of 38, and a mass number of 87. So the atomic number of 38 tells us most of what we're going to need. 38 is strontium there. SR. Oops. So this one really is telling us everything we need to know. We said it was 38. And it tells us the mass number, well, that's our A value. So we just throw 87, and it tells us our charge is 2 plus. So that one's really easy. It's basically all written down for you. And that's how you kind of determine the symbols on the periodic table of different charges that are there. The next one, this is one of the more tricky parts of the periodic table, is different isotopes. Because really, all of these atomic masses you see on here is AMUs. Where chromium is 52 AMUs, carbon is 12.01 AMU. Those are all averages. And they average all the different isotopes and their relative abundance, all the major ones at least. And we can take that average by summing up the equation here. We sum up the fractional abundance times that isotropic mass. So the isotropic mass is determined by the mass of all the compounds. So the neutrons plus the protons plus the electrons. The electrons are mostly insignificant because they weigh a lot less than the protons and the neutrons do. Well, the protons and neutrons are pretty close to being the same, but not exactly. So based on the composition of the different isotopes and the abundance of them, we can calculate out the average atomic mass. And we're going to do this here with lithium. So it says here that the isotropic composition of lithium from naturally occurring minerals is 7.5% for lithium-6 and 92.5% for lithium-7. I'm going to make a note of that. That's 7.5% for lithium-6 and 92.5% for lithium-7. And it also tells us the atomic weights of these two, respectively. So that would mean that the atomic weight of lithium-6 is 6.01512. The atomic weight of lithium-7, 7.01600. So all we need to do is add up the product of these two values. And when you take the percent, we move that decimal place 2 to the left, or we divide it by 100, get the same value. So I can write this as the average AMU is equal to 0.075 times 6.01512. I'm going to add that then to the product of 0.925 times 7.01600. And we're adding these two values together to find out what the sum of those are. We're going to do it in a couple stages though. We'll do one and then the other, because we have to worry about significant figures too. We're multiplying values together and then we're adding them together as well. So we want to find out what is our significant figure is going to be for each of these. So that 0.075 times 6.01512, that's going to be equal to 0.45, and I'm going to leave it right there because our 75 here, 7.5%, is really just two significant figures. And then we're going to add that to the product of the other one. So that's 0.925 times 7.01600, and that's going to be in this case it's 3 sig figs, so that's 6.49. 6.49. And we don't really want to do math with these rounded numbers to go forward. When we're adding these together, we want to use the numbers in our calculator. But I write them down there to show you the significant figures, because now we have to tourniquet this addition after 2 decimal places, which means it kind of works out for us anyways. But we want to include the decimal place, the numbers after that in our initial calculation, and then round at the very end. So I can do, I'm just going to pull the number from my calculator, I'm going to add that to the next number in my calculator. I'm going to say that's 6.94. We're going to round it after the second decimal place. 0.94 AMU. So that's the average atomic mass of lithium that's naturally occurring. The other part of this problem states that there's another commercial source from lithium which is recycled from a military source, which has a 3.75 lithium-6 percentage, with the rest being lithium-7. Well, how can we figure out those percentages? Since there's 100% in everything, we can say, so I'll write 3.75% lithium-6, and it's the same atomic weight as before, and then I can say the percentage of lithium-7 is really going to be 100% minus 3.75%, which in this case is equal, pull up our calculator, 100 minus 3.75. It's going to be 96.25, 6.25. In this case, we don't have to worry about significant figures because I can write this as 100.00 as well. It's the full amount. It's not, there's no uncertainty in everything. There's no uncertainty in 100%. And this is a percentage. So now we can go ahead and do that same calculation that we did before, where my average AMU is equal to 0.0375 times 6.01512 plus, and I can say 0.9625 times 7.01600. I'm going to zoom that out just a little bit. Try to fit my calculator in here. Well, it doesn't quite fit. We'll work with that. 0.0375 times 6.01512. So this is going to equal 0.2. In this case, 3 significant figures is what I want. 26. I'm going to add that to 0.9625 times 7.01600. That gives us 6.753. Notice I went 4 significant figures now because this guy is actually out to 4 sig figs. Our atomic weights of the isotope is going much more significant figures. But since we're tourniqueting it on the smaller one, we're going to stick with that. And I'm going to add those two values together. So that one plus this one is equal to 6.9. In this case, we want to end after the 3rd decimal place for each of them, so that's happy. 98. Next digit's a 4, so we don't round up. And this, I need my units. AMU. 6.978 AMU. So you see, it's the same compound, the same 2 isotopes of that compound, but because of the general abundance of them, they have a different average molecular weight to them, or average atomic weight to them. We can use this sometimes. There's many different isotopes. It could be 2, 3, 4. We usually focus on the major ones and don't worry about the small insignificant ones because they kind of get lost in the sig figs. Last thing I want to talk about today is the difference between empirical formula and molecular formulas. So the empirical formula is a formula showing a composition of a compound giving the simplest whole number ratios. Where the molecular formula is the formula indicating the composition of a molecule of a compound and giving the actual number of atoms of each element in the molecule of the compound. What that basically means is the empirical formula is the general ratio between those atoms. So we don't know exactly how those atoms are put together or on what scale it's at, but we know that this is the basic ratio of carbon to oxygen to hydrogen or something to that effect. Where the molecular formula tells us the exact chemical compound of that molecule. So in this case, we want to determine the empirical formulas of the following compounds, and they give us these molecular formulas to figure that out. And one thing we can point out is it's the simplest whole number ratio. So that means we take those little subtext numbers we find, and we want to find a common factor between them, and we can factor that out and give you our empirical formula. So for this first one, acetic acid, C2H4O2, we want to look at this 2, the 4, and the 2, and we look at what's the common factors of those. Really, it's a 2. Each one is divisible by 2, so I can say that the empirical formula is CH2O. For citric acid, C6H8O7. In this case, there's no common factors there. 7 is a prime number, which means it's only divisible by itself in 1. And since 6 and 8 are not divisible by 7, this has an empirical formula of exactly what it says there, C6H8O7. Hydrazine into H4 has a common factor there. There's a 2 and a 4, has a common factor of 2. I'm going to factor that 2 out and say it's NH4. That's the empirical formula. Nicotine, C10H14 in 2, well, those are all even numbers. They have a common factor of 2. And since nitrogen is a 2 there, we know it's the smallest, the largest multiple that it can have. So the largest factor, I want to say. Oops, I'm writing the whole thing down. I should be dividing everything by 2. C5H7N. And butane, C4H10, common factor of 2, leaving us with C2H10. And I lied to you earlier, there's actually one more thing, but this is the basic idea between empirical formulas, and you can scale that up to find a molecular formula if you know the mass ratios, which we can talk about in a couple of weeks, or a week or so. This is the last one, talking about whether things are ionic or covalent, and what are the different ions in there. So I'm going to write down my definitions of ionic and covalent bonds. It's kind of a Cribs Notes version. So ionic bonds is when metal reacts with nonmetals. Okay, and this is really what's happening here is we're gaining or losing electrons in ionic bonds. With covalent bonds, I should point out the key part of this is that a metal is reacting with nonmetals. So when we look at our periodic table, which I happen to have one here, we see the yellow ones are metals. So that's all of these over here. Stepping down through here and all through here. The metalloids are kind of this little strip down here. Those can really be either metal or non-metal. We usually treat them as non-metals for ionic bonds and covalent bonds. And the non-metals are everything in the top right. The white ones, they're really just super unstable, so they don't really exist for any lengthy period of time. They almost immediately react and become something else. When you get into isotropic decay, we'll talk about that. That's not till chemistry 223. But this up here is kind of like a Cliff's Notes version. This shows you what the common ions of all the metals are. Mainly, this group 1 and 2 metals. Group 1 is always going to be +1. That's this whole column over here. Group 2 is always +2. That makes it easy. Anytime you see a metal of group 1 or group 2 in your compound, it's going to be ionic, and you know what the charge is. Similarly, the halogens, group 17 over here, are always going to be -1. Group 16, with the exception of the bottom one, is always going to be -2. Group 15, with the exception of the 2 bottom ones, is always going to be -3. Carbon is always -4. So that is an easy way for us to determine what the charge is for things. Our noble gases, they're neutral, they're happy, they have a full valence shell of electrons. Our transition metals in the middle, they can have different charges to them. A lot of them have some common charges that are listed here. Chromium, for example, is commonly either +3 or +6, where cobalt is almost always +2, same with nickel, almost always +2, platinum, almost always +2. Silver is +1, zinc +2, aluminum +3. And you can get the gist of going through these as well. Copper can be +1 or +2. Those are both fairly common for them. So we can use this now to determine whether or not these are ionic or covalent, and if they're ionic, what is the symbols for those ions involved. Basically just what are those charges is what I'm going to go through. So this potassium chlorate, KClO4, K, potassium, lands on the group 1 metal, there. So that group 1 metal is going to be a +1 charge. So that means it's an ionic compound, ionic bond, and it's going to have a K plus and a ClO4 minus. That's really what's going on between those two. This next one, magnesium, Mg. So looking for a magnesium on our chart, we see it's right here, +2. And I should mention, this whole compound here has a neutral charge, which means if magnesium is +2, again this is ionic because magnesium is a metal. Ionic metals react with nonmetals. I never wrote what covalent metals do. Covalent bonds. It's when nonmetals react with nonmetals. So ionic bonds are when metals react with nonmetals. Since magnesium, definitely a metal, we know that magnesium is a 2+ based off our chart here and the fact that it's in group 2. That means the rest of it needs to have a -2 charge to keep that neutral. In this case, we have 2 of this C2H3O2, which means that C2H3O2 is going to be a -1 charge. And then 2 of those bonded to the magnesium, which is 2+, gives you a neutral atom. The next one, H2S. So you see S is over here. It's going to be -2 charge. H is supposed to be up here in group 1. It's not really in group 1. It's kind of just up there on the top because that's kind of where it belongs. But you notice that the S -2, it's over here in the metalloids, the nonmetals. So an H is a nonmetal too. That means it's a nonmetal bonding to a nonmetal. It's going to be a covalent bond. Our silver 2 sulfate, disilver, that's going to be silver disulfate. Again, S2 is there, but silver is over here. That makes it ionic. Silver's +2. Ionic. So Ag is a plus, and sulfur is a -2. 2-. Notice there's 2 silvers to balance that -2 charge on the sulfur. The next one has N2Cl4. Those are both going to be up here in the nonmetals. Right? Nitrogen is here, and chlorine is here, which means it's going to be a covalent bond. Last one, we have CO, that's cobalt, and NO3, and there's 2 of them. So cobalt, if we look for that, it's right here in the middle. It's a +2 charge, making it ionic. It's one of our transition metals. And that's going to be CO +2, which means that the NO3, which there's 2 of, is just going to be a -1. So that's how we can find whether or not it's ionic or covalent using our periodic table. And you see there's lots of things we can use our periodic table for. The common charges, at least remember that group 1, the group 2, 14 through 17, 18, those are pretty easy to remember. Group 1 charges are all +1. Group 2 all +2. 17 is all -1. 16 -2. 15 -3. 14 really carbon is -4. And then some of the common ones you're going to see here are your silver, your zinc, your aluminum, maybe nickel, iron, the 2 different charges of iron. They play a big role, especially when you get into acidity and stuff like that later on. and some of your gold maybe, but gold's probably not as important. Platinum is a standard one. So that's basically all I have for you today. I hope you got something out of it. Again, we're going to have these live streams on Wednesdays and Wednesdays and Saturdays. That's Wednesdays at 5 p.m., Saturdays at 2 p.m. And I'm going to try to have a kind of a group tutoring session after the Saturday meeting, probably right after it at around 3. So definitely try to check that out. If you have any questions, make an appointment with our tutor Amir. He's a chemistry tutor in Pendry. He's taking appointments as well, or stop into the group tutoring on Saturday and we can talk about things as well. Best of luck in this fast-paced summer course. There's a lot to go over. Definitely read your book, tune into lectures, and check in office hours. Have a great day and enjoy. Thanks.